All right, it's going to work on a structure determination problem. So in this one, you're actually not given the empirical formula. So you're not giving how many carbons, hydrogens, nitrogens, oxygens, whatever. But you are given some other different pieces of information. Right? Other pieces of information. So you're told something about IR and UV. So the first thing I'd look at, so you're told you have a UV lambda max. That's telling you that this molecule has conjugated pi bonds. Right? And the number's pretty low, so it's pretty short wavelength. So that would tell you probably don't have a lot of conjugated pi bonds, right? Remember, the more conjugation, the longer wavelength. 212 is pretty short as far as nanometers go, right? So I would guess I would have conjugated pi bonds, but probably not more than, right, 2 together, maybe.
Oh, really?
Yeah, so maybe 2 together.
Will we have something like telling us?
So you should recognize, if you recognize that this number is low in the UV range, right? 200 is low, 600 to 700 is high or longer. So that just gives you you should know that, right? 200 is a lower number, a shorter wavelength than 600. 600 would correspond to more conjugation, more pi bonds.
But is it like relative?
No, I'm not going to ask you to know specific stuff. Relative. I'm just all you need to know in this case is that you have conjugation.
Okay.
Done. What else is this telling you? The IR is telling you something. You have a peak at it says a broad peak at 3,000 to 3,580. I guess it's 3,580 here. It says you have a peak at 698 and then 981. So 3,000 and 3,500, what should that tell you? That's probably what? Broad peak? OH or NH? OH or NH. Good. The 698, what is that? 1698.
So
Cedo bondo, carbonyl. Right, and then 981 down that fingerprint region. What's that telling you?
that's
Transalkene. That's right, a transalkene. Right, squiggly lines. Right, remember the squiggly lines mean we don't know what it's bonded to. So I should have some squiggly lines over here. Right, so it's OH or NH. We have a carbonyl, and we have a transalkene. That's what the IR is telling us. Good. All right, so we know that part. So let's shrink this down a little bit, put that to the side. The other thing we know, it says the CI mass spectrum M plus 1 peak is M. So M plus 1 peak is 115. So if we have a M plus 1 peak equals 115, what's the actual molecular ion mass? So M plus 1 would mean you've added one thing to your molecular ion, right? So the real mass of the molecule we're looking for is 114, right? Because M plus 1 would mean you added one mass unit. So the actual mass we're looking for is 114. That's what that's telling us. Good.
So is that?
So if our molecular ion peak, our M peak is actually 114, right? Because our M is M molecular ion. So our actual mass of the molecule, the molecular ion, is 114. That's an even or odd number? Even. So how many nitrogens could we have? Even. So it'd be 0, 2, or 4.
Yeah.
I'm leaning towards, right, usually 2 seems like a lot. I would argue most times probably,
Because of the molecular weight.
yeah, no N, right? I'm guessing 0 makes more sense. I would start with 0, and if it doesn't work out, I'd go back and try 2, but usually if it's an even mass, you can be pretty confident it's 0.
So does that mean?
So then if we're taking that back, let's assume then in our IR we have an OH, right? We have an OH. So if OH is going to be one of our pieces, I've circled that in blue, let's subtract the mass of an oxygen and hydrogen from 114. So that would be 17, right? Oxygen 16, hydrogen is 1. 97 is what we have now, is our mass left over. So you subtracted out the OH.
Sorry, how did you get? Did you just guess? Oh, it's an OH.
Yep, so we're assuming there's an OH, we're assuming no nitrogens.
Okay.
We also know there's a transalkene, right? But let's wait to do too much more with that. Let's look at the NMR in a second. All right, so the next thing we looked at was our NMR. And this actually gives you the spectrum. This actually gives you the actual NMR spectrum. And so I'm looking at this and I see 1, 2, 3, 4, 5 different peaks. So I would say 5 types. And I went ahead and copied down from the spectra what was there. Oh, I actually skipped over. There's a peak way down. Let's call this peak F. There's a broad singlet at 11.9 ppm. Right? So there's another one there, that's 6. So I have 6 types. I have 6 types. So if there's any of these that like immediately like I look at and like, oh, I know what that is. That's what you'd want to do right now. And I think there should be one that you should look at and say, oh, I know what that is. Which one is that? Maybe that F at 11.9, a singlet that's broad.
Yeah, so is that like a carboxylic?
That'd be a carboxylic acid, I would think, right? So one piece I'm going to have then, from E, I'm going to have a carboxylic acid. That's HE. I don't know what's on the other side there, right? But from E, or sorry, not E, F, little f. Right, so I can check off F. And I can subtract out that mass from my total here. Right, so what's that gonna be? What's oxygen 1632 plus 1244 plus 145? Good call. We've already subtracted out the OH, so we can't subtract that out again. So this is C and the O. So carbon and an oxygen would be 16. 16 and carbon and an oxygen would be 16 plus 28. 28. Yeah, 28. So 28.
Would it be like 2 carbons though?
Nope. I don't know what's over here. Don't know what's over here. So we already subtracted the OH out, right? So we can also go back to our IR and check off, right?
Where did we get 28 from?
28 you got from 1 carbon and 1 oxygen. 16 plus 12, 28, right?
Okay.
So that would be from the CO part. Right, good. Little math here. 8, 1, 9, 69 left over. Right, so we found one piece. Very good. Now at this point, you could look. We also don't forget from our IR, right? We know we have a transalkene, and then all these other things are really there's just coupling constants for days. So this is telling us who's talking to who. So let's just look at E. At 0.9 ppm, it's worth 3 hydrogens. It's a triplet, has a coupling constant at 7.4. So there's other ones that have coupling constants at 7.4. So there's actually 2 options. Right? So which one's going to be the right one? Maybe I'm not sure just yet. But I know that there's a carbon that has 3 hydrogens on it. How many nearest, if you're a triplet, how many nearest neighbors do you have?
2.
2. So all these HEs, they're next to another carbon that has, right? It's either D or it's C. I would usually probably I would make it a little easier and not give you like the same coupling constant, right? But in this case, let's just pick one and see if it works out. All right, let's pick one and see if it works out. So let's pick actually there actually is one that's kind of obvious, perhaps, maybe not. Obviously, there's D, E, D, and C are all hearing each other, right? One of them has to be in the middle.
Yeah.
Which one do you think's in the middle? So, right, 7.4, 7.4, 7.4. If C was in the middle, so 2 of them are only hearing each other.
Yeah, so D.
D's in the middle. D's in the middle, right? Because obviously E's on the end. D would have to be in the middle because C must be talking to other people on the other side, right? So we've gotten quite a big piece here actually moving.
Can you explain that one more time?
I will. Let's go. So let's say, if we have E, D, and C, they're all talking to each other. Same coupling constant.
Yeah.
We know E is on the end because it's a CH3.
Mm-hmm.
But now we got to decide who is E next to, D or C. I'm going to guess D, right? Because D, if C is talking to other protons. If C was in the middle here, it wouldn't be able to do that,
Yep.
right? So it has to be D. Like I said, this is one of the more challenging ones.
Will we have something that's complicated on
You could. I'm not going to say you wouldn't. And then that would make this C. We don't know what's over there. So that's a pretty big chunk we just knocked off. D, E, and almost done with C. How many carbons was that? That was 3 carbons. So that's 36 plus 7. 36 plus 7 is 43. So you can subtract out minus 43 for that piece. So 26 left over. All right. So we have a whole carbon piece, carboxylic acid, this 3 carbon chain. We still haven't figured out where this is at yet, which this is going to fit in probably. That's right. Now it's kind of easier. The hard part was seeing that D had to be in the middle, right? Now these two must be what? They must be the hydrogens from that. Now it's higher, right? People will be like, well, it's 7.0, it's above 6.5. You said it'd never be that. No, I never said never.
So would that
Right.
be the vanilla?
So these are vanillic. Both of them are vanillic, and one of them is a little higher than you'd expect. But your IR told you what? You have a transalkene. So that's what these have to be, right? Some people say, well, there's an aromatic ring. It's like, no, there's not. You don't. No, there's not. Right? Your IR told you the functional groups. Stick to what your IR told you about the functional groups. Your NMR has to match it up. So both of these H's are part of this transalkene.
Oh, so the two peaks can, or,
And so one of them is going to be A, and one is going to be B. So now you have all your pieces, actually. You're done. Now the hard part is just putting it all together. There's actually only one way you can put it together.
On C, how do you, I don't understand like the quartet of.
So we'll get there. That's what we're going to talk about right now. So if it's C, if you look at C, it's a quartet of doublets. That means it has it's hearing 2 different songs from two different protons. If it has a quartet, how many nearest neighbors would a quartet give you? 3. How many nearest neighbors would a doublet give you? 1.
Wait, because it's itself plus the neighbor, right?
No, you have n plus 1. Yep, n plus 1. So let's just take a second, see if you can put this together and see if it matches up. These 3 pieces, see if you can put it together and see if it matches up. So the final structure then would have the carboxylic acid attached to the alkene at one point, and this 3 carbon chain also attached to the alkene. So let's draw that structure, and then we'll go back and double check to make sure everything we did makes sense. So what would that structure look like? We'll have the pi bond here, carboxylic acid. We know it had to be a transalkene, right? Had to be a transalkene. Let's label these. So we labeled the carboxylic acid one as F. Right? We knew this one out here was E. We called it the CH3 was E. This CH2 we labeled D. Labeled this one C. Right? Now let's look back at C. Right? So E has how many nearest neighbors? It has 2. So E would be a triplet. That matches up. D has how many nearest neighbors? It has 3. Right? 3 plus 2, right? So actually D should be a quartet of triplets, but they're calling it a sextet. They're kind of copping out. But if you're a sextet, how many nearest neighbors did you have? Sextet 5. So 1, 2, 3, 4, 5. So that makes sense for D. C is worth 2 hydrogens. It's a quartet of doublets. So over here, maybe it's not a quartet of doublets. C should have. C is really complicated. We'll not worry about the splitting as much. What about it? Was C hearing D? Yes. C is also hearing this proton and this proton, right? It's hearing all those guys. So why is this tough? 1, 2, 3, 4 bonds away. It's actually hearing something 4 bonds away. It's not impossible, it's possible. But the reason I know it is because look at the coupling constants. Look at C. C had to be talking to 3 different types, right? This C, there's 2 CH2s here, according to the coupling constants, was hearing 3 different things. So it was even hearing it 4 bonds away, probably because this alkene is not rotating, right? Do pi bonds rotate? No. So that's why this H is kind of just stuck here looking at C. So that's why C can kind of hear it sometimes. So C heard this proton and this proton. And I don't care if you know for sure which one's which. I'm going to label this one A and B. I'm not that concerned about knowing which one's A or which one's B. But these obviously would hear each other. Notice the coupling constant of 15.6, which told us also trans, just like the IR did. Remember, 15 coupling constant, 15 hertz was trans, 10 is cis. So that's the whole shebang here. Really the easiest thing you could do is not worry about the splitting as much and just look at the coupling constants would have been helpful. Especially for these ones that get really weird. I mean, E and D was easy to see the splitting, but on the picture online, like B and C and A, they're really some jagged peaks. It looks kind of weird. In those cases, it might just be better just look at the coupling constants. So yeah, the last little bit, why did the UV matter?
Yeah.
Where the UV mattered because it told us to make sure that our 2 pi bonds were right next to each other. We had to be conjugated. So is this a conjugated system? So you can go back to the UV and say, yep, check mark. This was a conjugated system. If I'm UV active, I must have conjugated pi bonds or lone pairs.
Again, conjugation is the pi bonds, but is it?
Lone pairs or pi bonds right next to each other. Yep, in a p orbital system. All right, so C6H13N. They actually show you the NMR spectrum as well, but let's do the IR, and then since we have the molecular form, we can do degrees of unsaturation. So what is the DU for this? DU is 1, right? So it means 1 pi bond or ring. So 1 ring, 1 pi bond, one of the two. IR, what is IR telling us? IR has a peak at 3280. 3280. So what could that be? Could be an OH and NH. It could be an alkyne SPCH, right?
Yeah.
Why is it not an alkyne SPCH? Yep, why? Why can't it be an alkyne CH? Because alkynes have 2 pi bonds, and we only have 1 pi bond. So it can't be an alkyne. So then it's OH or NH. So look at the molecular formula. Can it be an OH?
No.
No, because there's no oxygen. So the answer is, this is an NH. So we know we have an NH. 1653. That's close. And then, so 1653. C double bond O, C double bond C, C double bond N. It could be any of those. But then I see this peak at 898. What does 898 tell us? Terminal alkene. Mono or disubstituted? Disubstituted terminal alkene. So that's for sure telling us we have an alkene. So then that makes me think 1653 is probably a C double bond C, right? Because I can't have an alkene and a carbonyl because I only have 1 degree of unsaturation. So I'm guessing this is a C double bond C. It's a C double bond C, and I know exactly what type. It's a terminal disubstituted alkene. Terminal disubstituted alkene. Good. Awesome. Now we look at our NMR, and I see 1, 2, 3, 4, 5, 6 peaks. 6 different peaks. Let's write those out. All right, so how many different types do we have? Protons. So 1, 2, 3, 4, 5, 6. We have 6 types. So 6 types. So that's quite a few. That does make me think of symmetry at this point. That does make me think of symmetry. If we had, I'll label these A, B, C, D,
Wait, what did you say about
E,
symmetry again?
and F. A lot of peaks, right? So it does make me think of symmetry. I have 6 peaks with C6, H13. That does not make me think of symmetry, right? Because, right, symmetry, usually few peaks would be indication of symmetry, right? So in this case, I have 6 different types, so I'm not thinking about symmetrical here. Doesn't make sense. Okay, so kind of where to start here. Maybe the easiest one to look at, if you have a coupling constants, or go for that. Or I see this one that says broad singlet. right? A broad singlet. That makes me probably think that's my NH peak, right? So if I start drawing my pieces, so here's my NH, that from F. So I can subtract that from C6, H13, N. So N and H gone, that would be C6, H12 left over. I also can look and see here two things are coupled together. All right, so the next one I'd look at was the two things that are coupled together. So it's pretty obvious that these two things are coupled together. So this is where 3 H's, so that makes me think of a CH3, hopefully. All right, and so these would be CH3 and they'd represent E. E was coupled to who? It was coupled to C. So HCs. And I don't know what's on the other side there, just like I don't know this other side there. So we can subtract now that part from our equation. So that was worth what? That is C2, H5. So we have C4, H7 left over. So we can check off F, E, and C. We have a peak at 1.8. That's 3 H's. That's a singlet. That's D. So that's probably going to be a CH3 with no nearest neighbors, right? So for D, I would say D is going to be probably just a CH3. D's. I would say no neighbors here. So I can subtract C3, or C1, sorry.
Why are you saying that
H3.
C is CH3? Oh, because it's probably a allelic.
So I'm not worried about the frequency yet.
Okay.
I'm not worried about the frequencies yet. I kind of go back and look at the frequencies later.
Okay.
So now I have C3, H4 left. Is that correct? Yep. Good. So I've checked off D now. So I have 2 peaks left, a 2H singlet and a 2H doublet at 4.8. And now at this point you can, so maybe this for B, 3.2. So we know that's probably going to be a carbon with 2 hydrogens on it. And it should have no nearest neighbors, right? So that would be B. So you can subtract that piece out, minus CH2. So you have C2, H2 left. That counts as B. Now we always remember, like maybe we get kind of stuck, don't forget to go back and look at your IR. Like remember we have to have a terminal alkene piece at some point. So both those H's there are probably these 2 H's from this 4.8. So that piece would probably be this. These would both be A. And that's a C2, H2 piece. So we're good. So now we have our pieces. So we have 5 pieces. And now we want to look at the frequencies and try to make sense of where these things go. And also remember, right, things like B should have no nearest neighbors. Right? B should have no nearest neighbors because it's a singlet. D should also have no nearest neighbors because it's also a singlet. So where to put it from there? So go ahead and give that a shot. So yeah, good catch. The NH should have, the nitrogen should have 2 squiggly lines because nitrogen wants to form 3 bonds. So there should be another squiggly line there for the nitrogen. Good catch, right? Don't forget, carbon wants 4 bonds, nitrogen wants 3 bonds, oxygen wants 2. Right? Don't forget those basic things when you're doing these problems. Another thing to remember, OHs and NHs do not follow the frequency rules, like the shielding, deshielding. OHs and NHs show up wherever they want.
Oh, so
Carboxylic acid OHs always show up way downfield, but that's the only one we can tell. A regular alcohol and an amine, those peaks show up. The biggest thing, they show up wherever. The biggest thing to remember is that broad singlets. They'll be broad and singlets. That's how you know that they're OH or NH. Okay, so for this one, a couple key hints. So I know that these are A. So I know there's 2 branching points off this terminal disubstituted alkene. So the easiest way to think of what's going to come off of that. So what's coming off of that would be, right, these H's are vinylic. What's going to come off of those things are going to be allylic. So I look for the two protons that are close to the allylic region. Well, 1.8 certainly is, 2.6 is, and so is 3.2 is a little too high. So 1.8 is right in the wheelhouse.
What would that lily come out of that thing?
If you're coming off the alkene, right, 2 bonds away, you'd be allylic. So I'm going to say, for this one,
Oh, because 2 bonds are with it.
here's my H's, here's HAs. I'm going to say this one right here, that's going to be, which one should that be? That should be D, right? D is a singlet in the 1.8, which is the allylic region, right? So these H's, the H's that are in D, there'd be 3 of them, would be 2 bonds away from the pi bond, so that's the allylic region, so it makes sense that they'd be at 1.8. And do they have any nearest neighbors? And then 3 bonds away? Nope. Good. So what else should I build off of towards this thing? So if I'm checking off, let's see, I've checked off, so I got that piece in, I got D in. Now I have a nitrogen I could put right next to the ring.
But you just added one more hydrogen. Well,
Nope,
I guess.
nope. The nitrogen is bonded to 2 different things, right? So one of these things, if you were to bind to a nitrogen, what frequency would you be at close to? If you're bonded to a nitrogen, what would you be close to? And that region is 2.5. There's something at 2.6. Also, right, that C is at 2.6, so maybe C is probably next to that nitrogen, right, if it's at 2.6. So let's put, right, so we have, here is C, and then here is F, and this was, or no, excuse me, this was E, this is F. All right, so we're getting close. So we still don't know it's there, we don't know it's there. Check and check. Well, actually we do know now, it's done. What has to be between them? HB. Right, HB would have to be between them. So let's take a look and see, double check our work to see if that works. Oh golly. Whatever. So what's going to be, so if I put NH, so that would be E, C, F, B, D, and then both of these guys would be A. Now let's make sure that makes sense. Does that work? Right? E and C are coupled to each other. C is at, we said 2.6, so that makes sense, being next to the nitrogen, 2.6. D, we said, was allylic, had to have no nearest neighbors, that's at 1.8, so that makes sense. A's do. Now, why does it make sense for B to 3.2? That's like being near an oxygen. There's no oxygens. Why is B a little more D shielded here? Because it's both next to, right, it's both in that Z region next to the nitrogen, and also it's what? What else is B? It's allylic. So B is both allylic and next to the nitrogen. So it's going to be a little higher than you'd expect. All right? So that's like the tricky part of this. But even if you didn't know that, you could have got, right, hopefully these 2 pieces and then say, well, what's left? It's got to be, this got to be between them. Right? And by all means, write down your logic here. Write down like a sentence or words saying, this is what I'm thinking, right? Do that.